Okay, we're on the last question of assignment 19. This is question 111. So it looks like a long question. Don't be too distracted by all the wording in the question. What you're getting down to is that you're given the equation for the electrolysis of water. So H2O going to H2 plus O2. And importantly, you're going to have to get the two half reactions out of this. And this is actually a really good exercise anyway, because the either reduction or oxidation of water shows up in many other problems. We're going to go through reduction, oxidation of water just to get the full balanced equation. Now, so the first one, you can split this up in half. We do H2O to H2 being our first one. And first I want to know, is this oxidation or reduction? So let's look at our half or our oxidation states in this case here. So oxidation state of hydrogen in water is just +1, and in H2 it is 0. So in this case here, we're having a reduction. We're going from +1 to 0. So this is our reduction equation. Now, if we do want to balance this guy out, we can assume we're in acidic conditions. First things first, we need an oxygen, so we're going to put water over here. Now we're missing 2 H's. And so in order to balance the H's, I can't just add an H+. It doesn't exist by itself. H+ is always found with H2O. So for every H+ I'm adding, I'm going to add a hydronium and balance it with an equal number of water on the other side. So I need 2. So I'm going with 2 H3O+ on this side. I only wanted to add 1 hydrogen, so I'm going to have to add 2 waters over here to balance that out. And now we're at the time of charge. So we have +2 over here. I have to add on 2 electrons. So if we want to kind of clean this up a little bit, what we'll do is we can get rid of some waters here. Nicely, so we're going to have 2 electrons plus 2 hydroniums going to H2 plus 2 water. So there's our balanced reduction reaction. Now let's look at our next one, which is going to be water. I'll just kind of put it all in there. So we have water going to O2. So hopefully this one is an oxidation reaction, because the last one was reduction. And if you look at your oxidation states, O2 or O in water is -2, and in oxygen it is 0. So this is indeed an oxidation reaction. So let's start balancing this. My to balance our waters here, our oxidants, I'm going to have to put a 2 in front of this one. Now we have to balance all of our hydrogens. So we're going to need 4 hydronium on this side. And for each hydronium I have to put an equal amount of water on this side. Oops, not hydronium, water. Now let's look at all of our electrons. We are going to need 4 electrons over here. And is this all balanced now? Should be pretty good to go. So if we want to clean this up a little bit too, we can do that. You end up with, instead, I might as well do that, 6 waters going to O2 plus 4 hydronium and 4 electrons. So this was our reduction, this was our oxidation, and of course now we can add the 2 together to get our overall. In order to do that, you're going to have to take this guy here, multiply it by 2, add the 2 together. So I'm not going to draw out all of that step. But in order to get your overall, in this case here, you're going to end up with 2H2O going to 2H2 plus O2. So there's your balanced equation, which as you could have just easily balanced up here. But now you're seeing what's happening in each of these steps, because one of them can become important at any one time for other redox reactions that we're looking at. So I'm going to erase this now, but you have that all on your notes. And we can go to part A here. Okay, so now we have that out of the way. what charge is needed to produce 3.5 times 10 to the 6 liters of H2 gas, 12 bar, 25 degrees Celsius, assuming ideal gas law. So we are given a volume of hydrogen of 3.5 times 10 to the 6 liters. We have a pressure of 12 bar, and our temperature, I'm just going to convert it right away. Now we can use liters, we can use the temperature. We want to change bars into atmospheres, and our conversion for that, 1 bar is 0.987 atmospheres. So we can convert that right there. That ends up being 11.8 atmospheres. So from this, we can find our moles of hydrogen. We might as well get everything we have anyway right now. So I'll just kind of write it up here for now. Using our ideal gas law, we have PV over RT. So we have atmospheres and liters. So you're going to use little r, 0.082 times 0.08206 liter atmospheres per mole Kelvin. So you will get a number for moles of hydrogen of 1.69 times 10 to the 6 moles of hydrogen. Okay. The question wants to know, though, what's the charge needed to produce that? So from charge, obviously we need to know moles of electron is the most important thing. And if we know our balanced equation using hydrogen, or that half reaction that had hydrogen in it, we can get moles of electrons. So if you do look back to it, it was 2 electrons for every 1 hydrogen. So that means it's going to be equal to 1.69 times 10 to the 6 moles, and it was 2 electrons for every 1 hydrogen. We have 3.38 times 10 to the 6 moles of electrons. Charge is in coulombs. So in order to get our charge, our equation was the number of moles times Faradays, which is in coulombs per mole of electron. So after doing this, you should end up with 3.26 10 to the 11 coulombs. So pretty large number. That was part A. Now let's move on to part B. This. If the charge is supplied at 1.44 volts, we want to know how much energy is being produced. So it's important to know what these units of volts are. 1.44 volts is actually equal to 1.44 joules per coulomb. So if we want to know that, we know our charge, sorry, we want to find energy is produced, that's joules. And we know our charge, so we can easily just multiply this guy by the charge that we have. And our charge was 3.26 times 10 to the 11 coulombs. So we end up finding out that we can make 4.69 times 10 to the 11 joules. There's your answer for part B. B. Now C, what you're given is a combustion of oil. We have 4.0 times 10 to the 4 kilojoules per kilogram. We want to know the mass of oil that needs to be burned to yield the energy that we have up here. So this is, again, rather simple. We want to get kilograms out in the end, and we have a few joules. So if we take our 4.69 times 10 to the 11 joules, and we're going to divide by this one right here. Remember, we want to make sure we're in joules. So I'm going to do the quick conversion. That will be 4 times 10 to the 7, and that's joules per kilogram of oil. So from this, we can find out that we need 1.17 times 10 to the 4 kilograms of oil to burn to make an equal amount of energy.